Okay. Cool. Well, this is week 3. So far we've done the first homework and we have a second homework coming up. Okay. So before we talk about the homeworks, I'm just going to kind of review real quick what we did in class. The biggest thing we kind of went over was just Bayes' law. And it looks really complicated and sounds really complicated, but at the end of the day, it's really just saying, can we use some sort of prior knowledge that we know to take another probability into account, sort of. So if we're looking at rates of cancer and you get a positive test for cancer, how worried do you need to be? So you can tell that, we'll talk about this more specifically in a couple more slides, but it's also connecting the test given the actual value to the actual value given the test. So you know that if you get a positive test, the test is only, let's say like 80% correct, but you want to know if you do get a positive test, what are the chances that you have cancer? And that's the important question. So that's just really kind of what this all relates to each other. It's not too bad. So in statistics words, it's P of your hidden variable given your observed is equal to the probability of your observed given your hidden value, and then just to kind of normalize it out, it's multiplied by your prior knowledge over your average likelihood. So again, that's what you want to know is kind of the posterior. What you do know is your prior knowledge. You know the general likelihood, and then you want to kind of get also an average likelihood too. So again, I'll go through this with an example for cancer in a second. Yes, so those are like the basic terms, but like what do those actually mean, really? We never really kind of went over this in class, but I think it's a good thing to think about. There's two things going on here. Did your test say you were positive, or did your test say you were negative? And then there's also, do you actually have cancer, or do you not have cancer? So like one of these is way worse than the other one, independent of what your test says. So you really want to know, do you actually have cancer? And so if your test comes back positive, and it turns out, in 10 years they did some other tests and it turned out you did have a tumor or something, that's going to be called a true positive. The test accurately reflected the condition that you had. The other hand is that if your test said you had cancer, but you went another decade without having a tumor or anything, that's a false positive. So it was the opposite of the situation that kind of happened. So on the other hand, if your test was wrong, if your test says you do not have cancer and you actually do, that's even scarier than the other two options I mentioned. So that's a false negative because it reported that you had a negative result, but it was false. And then, just to kind of tie it all together, if your test says you don't have cancer and a decade goes by and you still don't have a tumor, then yeah, that's a true negative situation. So these kind of simplistically is what Bayes' law is trying to get at when it comes down to it. So with that in mind, and with our cancer example, we can kind of add some text to what we're doing here. So again, up here, that's Bayes' law in math, Bayes' law in English. I'll talk about this in a second. So what do these actually mean? Your posterior is what you're interested in. That's kind of the hard thing to calculate. So that's really just, do I have cancer? Your test can say one thing, and then a decade later, your genotype or whatever can say another thing, but at the end of the day, you're just in the moment, you want to know if I have cancer or not. So your likelihood, the thing that you do know, is your test. Your test either came up positive or your test came up negative. So that's the likelihood. That's your observable probability given what you know about the test. You can tell the rates of cancer just in the population. That's your prior. That's the prior knowledge you're trying to incorporate into this. And then it gets a little bit tricky, but on the denominator, the average likelihood is really just saying what's the probability of the test being positive in the first place. So that has to take a couple things into consideration. And as we saw in the slides, you can do this by by using information that you were given before. So you can use the, what do you call this? One of these is the multiplicative rule. That's from going from this part to this bit. And then you know just by definition that we said the probability of an observable or a hidden value is equal to the probability of that intersected with the positive hidden or observable, and then the probability of that intersected with the negative hidden or observable value. So it's kind of just, you can expand it out just by this basic definition here. We kind of skimmed over it in the slides. But so just on basic definitions, if you add the probability of the intersection of both the positive and the negative, it kind of equals just the probability. And so we can use that, and knowing that the intersection is equal to this bit, plus the same version of that, then you can use information you're already given just to answer the question, what's the probability that regardless of if they have cancer or not, they're going to get a positive test on their mammogram. So does that kind of make sense? It's easy to ask how often does this test come up positive, but if you're only given kind of like accuracies, or you get like a true positive this % of the time, you get a false positive this % of the time, you kind of have to back calculate it. But you're really just asking how often does the test come up with a positive answer or a negative answer. So that was Bayes' law, super fast. I mean, it's really just saying, if I know one thing, does the reverse equal the same thing? And it doesn't, so you have to use math to get to the reverse. There's tons of videos and examples online for this sort of stuff if you just Google it and look at YouTube or whatever. One of them was saying, given the fact that a Republican candidate typically passes a tax law, what's the probability that a tax law will be passed given whichever candidate is in office? You can kind of like flip the tables and ask, okay, well, we know he's a Democrat. What about the tax law or something like that? That was a very bad other example. But just, if you're thinking of cancer, you just want to know, do I have cancer or don't I have cancer? And all you do know is that you got a test result, and you also know that the test result is a certain % accurate, and you know that lots of people usually don't have that much cancer. So there's a website on the bottom of this, if you download the slides and click on it, and they give you numbers to all these things, and it kind of makes it more real when I see like a more visual example. But the numbers come out to be, even if you do get a positive test for this mammogram, it turns out that there's really not that much higher of a chance of you actually having cancer given the test result. And that's kind of what Bayes' law really gets into. So the website's pretty good. I usually hate when people show webcomics in class, but there's no reason to break the cycle. So this is XKCD. This is pretty much saying the probability that you're near the ocean, given that you're holding a seashell, is really influenced by the fact that you're holding a seashell. Like, when was the last time you touched a seashell? Probably at a beach, unless you're weird. So, chances are, if you're holding a seashell, you're probably at the beach. But if you just ask, like, when a normal person goes to the beach, that might be, I don't know, once a month or once a year, who knows. But if you ask them, okay, well, you know you're holding a seashell, where are you? They could say, oh, I'm at the beach. So that's this comment right here. But again, you can use that for test results or other statistics too. It's really powerful, but it seems like there's no real good explanations for Bayes' law. Okay. So before we go on, does anyone have questions about Bayes' law? Okay, well, if you do, ask them later. All right. We also talked about building models and building these sort of information graphs. And doing it on the homework or doing it with real examples is a little bit confusing at first. So just using a really simplistic example, there's 3 conditions in this situation. So one condition is that it might be raining. You kind of want to know, is the grass wet? And then another condition that could make the grass wet is that the sprinkler is on. So if you want to build a model of this, you can say, okay, well, if it's raining, the sprinkler probably isn't on. And directionality in these graphs kind of means it's influenced by the other end of the arrow. So the grass is being wet is influenced by if it's raining or not. The grass being wet is also influenced by if the sprinkler is on or not. And unless you're wasting a ton of water, the sprinkler being on is usually influenced by if it's raining or not, because if it's raining, you don't want to keep on the sprinkler. So we have 3 nodes of this graph and 3 kind of directionalities of influence. But it's very simplistic, and it's useful because if you look at this, you can say, well, just by pouring a bucket of water on the grass doesn't mean it's about to start raining. That's what these arrows kind of indicate. So these are going to be a little more complicated when you're using the models we do in class, but the arrows is like a directionality of influence, and the nodes are kind of just conditions or genotypes or whatever you're really trying to model. Something that can be influenced by something else could be a node in a model. So that's just what these graphs are. Okay, so I said it would be a quick review of the stuff we did in class. I'm going to give another quick review for the homework stuff too, and then you guys can start asking questions. Is that fine, or do you want to just start asking questions now?
Can I ask a quick
Yes. Sure.
Okay, so this is probably really stupid, but so we started off Wednesday's lecture where we had like the probability of H is a probability of H in a set S, so we use that variable S.
Yes.
But then as soon as he got to face off, we never see that variable again. So it, like, can I just ignore that forever?
Yeah, when you there's a difference between probabilities and sets. So the set of all things that can happen is being described in each of these probabilities. So you go from like the number of events, which has to have a numerator and a denominator, to just the fraction, which is the probability.
Okay, so what you're saying is like this thing is likely, so it's by default already accounts for that S variable.
Yeah.
Okay.
Yeah, anytime you give a probability, it has to consider your solution space, which is the S. Did that make sense? Do you want me to pull up the picture? Okay. That kind of has to do with, and I forgot to mention it, on the courselets I put up a couple like statistics questions, and instead of working with probabilities, like this Bayes' law is talking about, it works a lot more with like the actual sets and like the number of events happening at like intersections or sort of statistical things. So when you say like which parts of the Venn diagram are the numerator and which parts of the Venn diagram are the denominator, that kind of, I think, clears it up a little bit more, or at least gives you like a visual representation. But if that was still unclear, just ask me about it in a minute or so. Okay, the homework. We use a couple type of like statistical models in this class, and we went through them pretty briefly in the slides, but I'm just going to kind of go over what these mean real quick. So a binomial distribution, when you define it, you usually define it with like 2 parameters. There's the number of trials, which is n, and there's the probability at each trial, which is p. But what a binomial distribution does is just saying, like, if I have a coin and there's a 50-50 shot of heads or tails, if I flip the coin 2 times or 4 times or 8 times, how many times is it going to come up with a heads answer? So I'll show a graph of that in a second. But to put it in words of the homework, this line is directly out of the homework, and we say that the probability of having a certain copy number, that's this bit, given the population mutant frequency, so that's kind of like the probability of each trial, the F. So given a frequency of this mutation, what's the chance that we're going to have a certain copy number of it? That's equal to a binomial distribution with the number of trials is out of 2, but you're asking if I have a copy number of 1 or a copy number of 2 or a copy number of 0. So this kappa is really what you're going to look at. So you have to ask, do I want to know if the copy number is 0 or the copy number is 1 or the copy number is 2? But we can just kind of extract it or abstract it to a variable. So we're saying whatever the copy number is, the number of trials is 2, and at each trial or on each chromosome there's a frequency f that it's going to be on there. So if you do this on the coin flip example, your f is like, do you have a weighted coin or not? So it's your chance of heads or your chance of having a mutant allele is your probability, and your number of like flips or your trial number is just the number of chromosomes you have, which in this case is 2, because we're people. So if you're talking about coin flips, if you flip a coin 20 times, and for some reason there's a quarter of a chance that it's going to have a heads, it's a weighted coin, you can use the binomial distribution to show that if you flip a coin 20 times and there's only a quarter of a chance it's going to be heads, you're probably not expecting it to be heads every time. But using the binomial, you can say, well, we probably expect to get 5 heads out of 20. And we can also ask, what's the probability of getting 7 heads out of 20? And that's about, I don't know, 11% chance that if you flip a coin 20 times, that's weighted. Then if you're looking for 7 heads, it's about a 11 or 12% chance. So that was a little bit slower than we did in class, but binomial is just asking how many, what's like the expected number of heads you're going to get when you flip a certain number of coins at a certain probability. That's opposed to the normal distribution, which we talk about a little bit further in the homework. And the normal distribution, as we'll see in a second, I'll show a picture, but you describe that as a mean, which in this case was a fluorescence reading from a chip that they use. And then biology is kind of noisy, so there's always this standard deviation or kind of variation from what you expect. So with the normal distribution, in class we're saying we have a certain copy number. Let's just make it like a not abstract example. So say we have 1 out of 2 copies of an allele. You kind of expect your fluorescence to relate to that, because if your chip is trying to tell you what's the percent of fluorescence it has, then it should be reflective of what the biology actually is. But the idea of like having hidden variables and observed variables is that you don't really know the copy number. You can only guess at it by probability. So saying you have 1 copy of a mutant gene and some sort of noise thrown in the equation, the normal distribution says usually you expect your fluorescence reading to reflect that you only have 1 copy of the gene. Because it's statistics, we do it, everything is always out of 1 with probability, because you have like a % chance. So it's divided by 2 because we have 2 chromosomes. So if there's 1 out of 2, it's 50% of the fluorescence that it could be. If you have 2 mutant alleles, then this test would give you 100% of the fluorescence, and that comes down to a 1 because it's divided by 2. And again, we consider some sort of noise. So the probability of getting a certain fluorescence reading, given that the true copy number and a certain amount of noise of your biology, can be described as a normal distribution centered around the true copy number, but it does deviate a little bit on either side. So what does that mean visually? Mu, again, we said was the mean. This would be like the most probable copy number. And then on either side, there's some sort of noise going on. Your fluorescence could give you a 0.4 reading. That's close enough to 0.5 to where you can guess, okay, well, there's probably only 1 copy. And then, as you'll see in the homework, you can add distributions to each other, and they kind of form these little camel bumps. So when we had a summation sign in the homework, that was just saying we're going to add together 3 separate probabilities and get the number from it. So again, the peaks are pretty low between the big peaks because there's a pretty low chance that you're going to get like a 0.3 reading from, if you're either looking for a 0 or 0.5 or a 1, then the chances of getting stuff in between is going to be accounted by the noise in your biology representation. So Does that kind of make sense where you can like add distributions and it looks like a little wavy line? I should say on the x-axis, the bottom, these numbers are your copy number. Or actually this is the fluorescence on the bottom. So on the bottom this is what you observe, and then on the y-axis is your probability. Yeah. So in this case, we say that the frequency of this mutant allele happens 20% of the time in the population. You want to say, what's the probability given some value, and you can just iterate it over the entire thing just to get this graph. But at any point, you would put like x equals 0.2, or x equals 0.5, or x equals 0.8, and then your sigma is just how much kind of noise is thrown in there. That's your standard deviation. Because biology is messy. Okay, so those were real quick 2 distributions. Yes?
Why is the probability so big? Like, why does it go above 1?
Yeah, I'm not sure. That, yeah, I don't know. I can come up with an answer and get it to you in office hours. I could have just done this graph wrong, but I think there's a real reason to it.
So it's like
What's that?
when you plug it out, and stuff
Yeah. Yeah, I don't know the answer. Sorry. Yes.
just a semantics question.
Sure.
So I saw, like, before you wrote everything with the sub I, like, what does that mean?
You're talking about this
Have
bind.
the sub I, yeah.
Yeah. So it really just means like the number of your copy number, kind of. So it's. Oh wait, that's not true. In the homework, we're looking at multiple genes or multiple single nucleotide polymorphisms. So your I would be the current one that you're looking at in that scenario. So for each gene, there's a kappa associated with it, there's an F associated with it, and you would get some probability of that. Yeah. So any other questions? Yes.
If we go back to the graph,
Sure.
just interpreting the graph itself, this is telling us that given a frequency of like 0.2 and an amount of noise that we just set at 0.1,
Exactly. Yeah.
that the probability of getting a certain fluorescent signal is going to be defined by this.
Mm-hmm. Exactly. Yeah. So. Oh, sorry. Yeah.
So say you get like a signal of 0.4.
Yes.
So the probability of getting a signal of 0.4 would just be like, say, 0.7, for example, if you read off the graph.
Yes.
What is that? Does that really tell you, based on this distribution, is it saying that you're more likely to have one copy of the mutation, or like what does this really inform how many copies of the mutation you have? Does this tell you anything?
Let's see. The answer is yes. I just don't know how to kind of describe. You're really asking. It's a little bit confusing because in this graph we're talking about kind of the opposite. So we're saying, given you have one copy, what's your fluorescence? And then if it's 0.4, there's like a certain chance that it's going to come up as 0.4. Just like if you flip the coin, there's a certain chance you're going to get all 20 heads, which is very low, or there's a certain chance that it's going to be, okay, say there's like 10 coin flips. So that's kind of what this is getting at here. So if you get 4 out of 10 coin flips, there's going to be a high chance of that because it's kind of close to that bump that we described in the other slide. So if you yeah, I think this is kind of total probability where it's saying what's the chance that a 0.4 reading is going to happen at all. And it's only going to happen, I mean, it can happen when you have 0 copies, but it can also happen when you have 1. And that's why it kind of peaks towards the moon. Yes?
So is this probability like the prior in Bayes' law then?
Uh,
It's like the probability that it would happen. You know,
I don't want to give you the wrong answer, but this is like your observable kind of, because this is what you're observing, and then what you're observing given the number of copies would be your prior. No, that would be your that likelihood. So I think these are likelihoods. Yes.
Sorry, can you just define the axes again?
I think this is a certain fluorescent reading on the bottom, and then this is some sort of probability of that coming up at all. I think that's right.
could it be flipped for the probability? Like, between 0 and 1, and then the resistance is between 0
I think it's probability.
So you would get a higher fluorescence if you have more copies.
Well, in this case, it only happens 20% of the time in the population, so you get a higher fluorescent signal if it's around 0, or even if it's around 1 copy. So on this axis, it's saying how likely is getting that chance, just in general. And then on the bottom axis, you're saying, okay, I saw a fluorescence of 0.3. That's kind of weird, because that's between getting 0 copies and 1 copy of the gene. So how likely is that? That's not very likely, because it's at the bottom of this dip between. You should expect if you have 0 copies, it comes up with a 0, and you should expect if you have 1 copy of the gene, it comes up with a 1 in the center, or 0.5, yeah. Does anyone get it that wants to give like a more clear definition? Does everyone not get it? Is that okay? So instead of complicating it,
Sorry.
Well, is the reason that the y-axis goes above 1 because you're summing probabilities? So is it
yeah, but you would
because-
think you normalize it at some point or something.
All right.
I haven't looked at like the code and what it's actually doing. I mean, I don't want to tell you the wrong thing, but they could also just be like percentages, kinda, but not really, because those percentages didn't make sense. So ignore that I said that. But I think it does get kind of weird because you are summing over 3 scenarios. So I mean, yeah, I don't want to tell you the wrong thing, but it would make sense that if you're adding 3 numbers from 0 to 1, the highest number could be a 3, and so if you get a 3 on this graph, that's an 100% chance that it's going to happen. I think that's probably what's going on, but I don't want to tell you the wrong thing of what's actually happening. Did that kind of make sense? I think if you divide all these numbers by 3, it kind of makes more of a statistical sense. Okay, but I don't know for sure, so don't quote me on that. I can come up with the real answer next week. I didn't dig into it too much. Yes?
And just to make sure I'm not over-interpreting, there is no direct biological limitation. This is just a model of 0 copies of mutation, 1 copy, or 2 copies. Like, if I chose some X value between 0 and 1, it does not mean that you got like half the copy of the mutation.
Exactly.
Possibly.
Yeah, it means you would only get that number through noise, and the noise gets less and less likely the further away from your expected number. You guys said you do like protein stuff in your other classes. You guys are protein people. So let's say you had like a column, and you know that something binds to the column. If you now I don't know how to put this number, but let's just say it either binds or it doesn't bind, and you know through like the literature that you're expecting something to bind, and you put it through the column, and it does bind, and like 90% of your protein binds to it. That's what you expect. If you put it through the column, and only like 30% of your protein binds to it, then that means you either screwed up your column, or your protein isn't as interactive as you thought it was. which is contradictory to what you're expecting. So at every kind of vertical slice in this line, it's just saying how likely is getting a fluorescence measure on the bottom axis. Another question?
I don't know if I'm allowed to ask this, but would we be able to go through the pixel that was given and like?
Yeah, it's already on your computer.
Yeah. It was just like one of the steps I don't know.
Sure.
If the x values equals I.
Okay, yeah, let's just go into that. Also, did you guys get my announcement last night about you should use these functions for parts 2, C, and D, or whatever? Yes.
Is there a command in Python where we can just pull up all the function next time instead of like?
Yeah, there is. Okay, so I'm going to pull up my VirtualBox. So in the beginning of the homework, there was like a help command, I think.
Yeah.
That's what shows you everything in your library. Or maybe it was the dir.
Right when you type in the directory, it tells you like all the different functions that are present.
Is,
You have to tell it to print though.
I don't think it gives like which one we're match and mismatch command though.
I'll show you in a second.
It says after you type the directories here, it says like this one. So it's this is the virtual.
Okay, but so while this is booting up, which question were you asking about? What was the question?
Okay, it was about like constructing the x values for the first set of graphs. So like x vals equals
Okay,
I.
yeah.
I think he just explained it to me. It's just
Well, what was the question so other people can hear it?
oh, the question was what's the line x vals equals bracket I times another one for I range.
Yeah.
That one.
Okay, and you cleared it up? I mean, it kind of just reads like it says. So your x values is a number multiplied by 0.01, just because you're going to go from 1 to 100, for every value in the range of 1 to 100.
So I just means like a distinct value.
Yeah, that's your like container variable, or that's just where the number's going from the range. It's going to say at each point in the range, put it somewhere. So you're putting it in like a variable called I. And okay. So again, we're using code from class. I'm going to make this bigger. Can you guys see this? Is this readable? Okay. Kind of hard to read the black background with white text on a screen, but if it hurts your eyes, just let me know. So we import all the code that Dr. Lee already gave us. We can use, if you want to see everything that he gave you, you can either read the file or you can just kind of get a summary. So getting a summary is the command dir with whatever your library, or I think this works with like functions or pretty much anything. You can ask about what's in it, and that's the dir command. So you get, it's in alphabetical order. The first one is the odds calculation, which I can talk about in a bit because I don't think we talked about that too much. There's something called stats. I don't know what that is. We don't mention it. There's something called sum p of x. That's what we use in the first part on page 2 of the homework. And then these other two functions that we forgot to tell you about until yesterday is the sum of the match model and the mismatch model. So that's how you would have known to do it. We didn't expect you to know that. There was actually more in the homework that we took out, and it included the part where it talked about those two other functions you should use. But in the prior version of the homework, it wanted you to open up and go by line what it's actually doing and then change some stuff. So we thought that'd be too complicated. But when we took it out, we also took out the part that we mentioned that they exist in the first place. So sorry about that. That was on us. Anyways, so the dir command is what you were asking, just to see what's in your library. Okay, I'm gonna also, I had a slide on the odds stuff. Okay, but just some definitions. So when you're asking like P of X, usually we're talking about discrete variables, which means it's not a range from like 0 to 1 or 0 to something. It's always like 1 coin flip or 2 coin flip or 3 coin flips. You can't have a half coin flip. So those are discrete variables. When you talk about continuous variables, those are like fluorescence readings and stuff like that. So you can get 2.5 whatever units fluorescence are in. And because of the calculus behind it, you have to look at ranges. You can't just look at a single point in these graphs. So with a discrete, you can ask what's the probability of like 3 coin flips. With a continuous function, you have to say what's the percentage of the fluorescence below a certain value, or what's the probability it's going to be above a certain value, or something like that. So that's what this calculus is. They kind of mean the same thing. The idea gets a little funky when you're talking about continuous variables. If you add up at every point, then you get the cumulative distribution function. Those are the graphs that kind of like keep increasing until they level off, sort of. And the reverse of that is like the survival function. So if you have like 20 mice in your experiment and you plot out how many of them die, at the end of your experiment, if there's still some mice that survive, that's going to be like your survival percent is like 3% if you're doing some really rough cancer stuff on the mice or something. So cumulative is kind of like the total sum of like what happened in the entire experiment, and then the survival is kind of like 100% minus how many of your mice died, sort of. So these were also just kind of skimmed over. But what I really wanted to talk about for the homework was this odds ratio. And it's really just, you put two models on a fraction, and if your odds ratio comes out at 1, that means both your numerator and your denominator are like equally likely based on the data that you just gave it. If your odds ratio is greater than 1, that means that your numerator, in this case it's the match model, is more likely or more described by the data point that you just asked of it. And if it's less than 1, that means the denominator is bigger, and that means the mismatch is more likely based on the data you just give it. So in the last question, it's going to ask you to give another one of those confusing plots between two ranges of data, and you're going to answer, well, between this range, actually I'll just, oh, I didn't include it. Well, yeah, you kind of just describe when does the plot go above 1 and when does the plot go below 1. And if you've been doing the code correctly up until that point, it's really just a matter of switching. You just replace the word sum p of x with odds, calculate odds, or whatever that function was. So in practice, it's pretty simple because you're just replacing a word, but the idea of an odds ratio is a little bit different. So did that kind of make sense with the odds? S is your suspect's copy number, I believe.
It's the other sample. X is like one sample and S is like the other sample.
That's correct.
Wait, so X is in the fluorescence.
They're both fluorescents of two separate samples. X is of like what you're comparing it to, and S is like the suspect.
Yeah. So yeah, you have two samples, and you want to see if they like match or if they mismatch based on these two models. Okay. So that was all I had for the review. The rest of it just asked. Do you guys have questions? Yeah, your question first.
Sorry, can you go back to the last slide?
The odds ratio one?
Yeah, I'm just trying to conceptually understand like just looking at the numerator by itself, like what does this mean? Like probability of the like fluorescence of the suspect and at the time. See, does this column means like the intersection of the two, right?
Correct. And I think when you write it like this, you're kind of just saying, you consider your x, you consider this based on the frequency of the population. You also consider the noise, and you also consider the model that you're using.
I guess I get the given part. It's more the stuff that like precedes that. Like conceptually, what does that mean?
You mean why are we using commas here?
Sure, I guess that's part of it.
Okay.
It's like the probability that these fluorescences are what? Are equal to something, I guess.
I think it's equal to each other or not equal to
To
each
each
other.
other.
Yeah.
But this comment is getting at equality.
Yeah, you're saying our model contains that we're going to look at the original fluorescence alone, the other fluorescence, but you want to know it based on the population, and then you also want to consider kind of the noise. It's kind of just saying you can. All of these things are included in the probability of what this outcome is going to be. In the slides, there was the different information graphs, and it showed the model on each of them. And so it's really just more combinations of conditional probability thrown in there or not thrown in there. I can pull that up in a second if you want. Yes?
So on the same note, so it's telling you what you're taking into account when you're taking the probability for the numerator and the denominator, right?
Yeah.
But then, so for x sub I, should he also take into account like the frequency in the population? Like I'm not sure why you would just take into account the frequency with the
Yeah.
s sub I.
I'd have to think about that and get back to you. But I think it's more related to kind of the multiplication rule.
Okay.
Because once you
I'm
know
still
one,
trying to go through how you derive
Mhm.
how to derive the equation, so it probably relates to me not fully understanding that.
yeah,
So,
I think that's kind of like this bit
okay.
over here. Because if you're assuming like independence or not independence, I think that's what's being thrown in there.
Okay.
Okay. Yes.
So like for our homework, we were given X, and then like we're supposed to for S is like a range. How does that work? Because like shouldn't we have like X is the fluorescence of one person, S is supposed to be a fluorescent of another person.
Mhm.
So why is the suspect we're giving the interval of his fluorescent measurement, but for X it's just one fluorescent?
You could do like a 2D plot and it'd be really messy to look at, where it would give you like a 3D curve or whatever. But so these aren't saying that the stuff is changing. You're just saying that in each instance on the x-axis, you're saying what is this probability. Let's see. So, and I forgot your question. I'm sorry. But so in this one, you're just saying what do you expect when you see a fluorescent value. It's not saying that your microarray is giving you a range of fluorescence values. You're just saying that if I ask you, what's the chance of getting a 0.4, you can get a number. And then I ask you, what's the chance of getting a 0.6, and you can get a number. And if I ask you that like a million times, it's going to start blurring together and look like a line continuously. Did that kind of make sense?
Sort of.
Okay, so I can pull it up, but if you have where's the homework? Okay, so in one of these, before you plot it, in this one, you give it F. That looks terrible, I'm sorry. Okay, here. Not great, but so you assign F equals 0.2. You assign sigma, which is like 20% of the time people have this allele, and there's a 0.1 standard deviation to it. Then you say, what's the chance of getting a 0.1 fluorescence reading based on these two numbers? So that's the first thing you do, and it spits out like a certain probability. And then what you do is you plot it. So you give it a range of x values. So you're saying, what's the probability of getting a 0? What's the probability of getting a 0.1? What's the probability of getting a 0.2? or 0.3, and you do all those numbers all the way up to 1, and then you just plot each point on the graph, and it gives you like a little curve to it. I'll keep explaining it in a second, but what was your question? I'm sorry. Oh, okay, sorry, if it comes back to you. So does this part kind of make sense, where you ask, okay, if I ask what's the chance of getting a 0.1 on this fluorescence reading, it's going to give me like a probability to it. Does that kind of make sense? If you go to the graph, then we're saying, okay, pretend we have a line here in the vertical. That's all we asked in the first place. What's the chance of getting a 0.1? And it comes out to about a third of the time that happens, given your noise. That's kind of all it's really asking. But you can display it as a graph just to kind of consider everything at the same time. I don't know if that really explained it, but
Yeah, I got it.
okay. Yes.
I guess the question is more related to the code itself. How do you graph 3 lines on the same one? I did it in a form, but
Oh.
I think there's.
I think if you just don't show it or print it somewhere, then it. Okay, well, in the homework on page 2. Oh, I had it pulled up actually. Okay, so on this bit, it says figure, and then it says plot, and then it says show. But I think if you say plot to other things, then it also displays it on the same plot. Do you want me to try to do it for you?
Well, I did it with a form.
I mean, as long as it works, it works.
Doesn't the pyplot figure that command just says make a new figure?
Yeah.
So if you don't type in pyplot figure and then you just put in whatever you want to plot, it'll plot on the last figure.
Mhm. Yeah, correct. Yeah.
Does show delete the figure though afterward? Because whenever I use show and then I plot them again,
Yeah, it's blank. It does delete the figure.
it does.
Yeah, you kind of either have to say put it to a file or show it, but it's the order matters
So
when you
it,
do that.
so it's recommended to save the figure before you show it.
Yeah, for all of these, I would just save them, and then you can just open up like the visual browser and go
Okay.
to your homework folder. Yes.
So for question 2, 2D, it says to hold the value x. Like, what is that? Is it talking about big X or like X? Because how can you hold X when you're plotting it as a function of S from 0 to 1?
You're just saying x equals to 0.5 at every point in your graph.
So like
So if I asked you, what's the probability of x being 0.5, s being 0.5, f being 0.2, and sigma being 0.1, you can just plug that into the function, and it gives you like a probability. And then I can say, okay, now what's x equals 0.5 and s equals 0.4 or something. So the only one you're changing is s. You could change both at the same time, but it just makes a really messy plot.
So I mean, are we still plotting the same like X vowels that we defined before?
Yes.
I see.
This time x vowels means s vowels. Sorry. Okay.
I started calling them S vowels instead.
Yeah, well, I mean, it doesn't mean the x-axis. It means we have two things called x in this scenario. There's the x-axis and there's the x fluorescence reading. But in this case, there's the
That's fine.
s fluorescence reading.
And that becomes your x-axis.
Yeah, correct. So if I say, what's the chance of having a bag of apples and oranges, and there's 2 apples in the bag, and there's 4 oranges in the bag, what's the chance of pulling out an orange? And then I can ask, well, what's the chance of 2 apples in the bag and 5 oranges in the bag? What's the probability of pulling out an orange? So I can ask this 100 times, and I would always say there's 2 apples in the bag. And that's like fixing the value of apples at 2. Is that kind of... Yeah, this is all statistics stuff. Okay, I think we have one more question we can ask, and then we're out of time. But if you're still confused on stuff, definitely come to the office hours and I'll run through the code and I can try to come up with like code examples of what makes more sense to you guys or something. Okay, well I guess I'll either see you at office hours or I'll see you Wednesday.
Yeah, so